What's up, everybody? My name's Clay Anderson. I'm joined here by my good friend Dom Donato, varsity baseball star. I also have a state-of-the-art trebuchet that I built myself along with Hayden Craig. Shout out. Put a lot of work into this bad boy. So today we're going to have a little bit of a challenge. And I'll teach you all about this thing too, but challenge is more important, I think. So I'm going to throw this, and he's going to throw his baseball. Let's see which one goes farther. Make your predictions. I'm going to go first. Alright, so pause the video to make your predictions now. I'm thinking this bad boy is going to beat him by a mile. You want to count me down?
3, 2, 1. 3, 2, 1.
Alright, Dom. That was pretty dang far. Let's go check it out. What do you think?
I think I got you. Except I hit branches all.
I also hit branches, so. By the way, the neighbors are totally cool with this. I checked with them earlier. True. Yeah, this one's mine. Went to this tree here. I think his one farther. That's about, what is that, like 20 yards? Give or take?
15, 20 yards, yeah.
All right, so we're gonna add more weight. See if I can out throw him. All right, so in light of that failure, I took off the 210s and 25s and added 225s. So now we're at 75 as opposed to 55. So that 20 extra pounds of potential energy should launch ours a bit farther. Hopefully we can get those extra mileages and beat Dom. So let's get it going. 3, 2, 1. 2, 1. Oh my God.
Holy sh**. I don't know if I can beat that. All right, here we go.
Yeah, I think I got him there. Let's go check it out.
Oh!
What?
Let's go.
Dude, that's the same.
No, it's not.
I don't know. I think you moved a little bit in front of the
No, I didn't.
arm.
Let's look at the video and see what we release further.
All right, so I slowed it down and I looked at it, and so basically what I'm looking for right here is for the pin, where the point where the pin is released, is you can't see the top of it, and it's right around here. All right, right there. All right, you see, here you come in. You can see kind of right there. Right here, the pin is released. Right there on this frame. So somewhere around here is where the ball was released. And then we look at Dom, so this is our plane. Here's Dom, and his is just about the same plane. So he beat me. Congrats to him. I call that pretty darn good. That's what I call that.
That's good. That's science at work.
Science at work right there. All right, so let's discuss the physics that lets this thing throw as far as a West Point commit.
Not as far.
A yard short of a West Point commit. So the basic parts of this is the counterweight, the fulcrum, the lever arm, and the sling underneath here. So when the pin is pulled and the thing is free to drop, this thing falls, the lever arm flips up, and then the string comes around. So right here we have, this is where physics come in, we have a lot of energy stored up here because I had to pull this thing down to load it. So this is stored up here. This is like 22 kilograms, so 200 some joules by whatever the height is. It's a lot of energy. So when that falls down, the energy gets transferred into this, and then this, as it's getting flipped up, because if you see the video, it doesn't flip up like incredibly fast. So if you just put it here, it wouldn't go that far. But if you, since you put it in the sling gets shot out. The string is under tension, the centripetal acceleration from like the movement of it causes it, yeah. So, and then the angular velocity of the ball shoots up until it releases, and then that angular is just straight to linear, and that goes super far. So let's talk about some stuff over here. Down here we've got the release mechanism, which is just a screwdriver through a few loops on either board. And then here is the most important part, the pin, which one of the strings on the sling is attached to this thing. One's hooked on down here, tied in, doesn't move. But when this gets to the right angle, this will actually like release and it'll open the sling up. So I'll demonstrate that just a little bit without, oh, lost the ball. So I have the ball in the sling. So imagine this is getting flung that way, but I'll just toss it straight up. So the pin comes out, the ball goes out, and obviously if this was a proper launch, it would go that way. And then finally, let's look at counterweight. We've got this counterweight on a pivot, and that's for a very specific reason, because you might be wondering, why not put all the weight up here? It's a lot higher, so there'd be more potential energy, and there's a pretty good reason behind that. Now, if I built this a different way, I could demonstrate that a little bit better if I could put it up here, but that'd be really tough. I don't think I can do that. So I'll just try to demonstrate like this. So basically, the point of having it like this is to allow the lever arm and the this thing to be a complete stop. That way all of the energy can get transferred into the projectile. That clearly doesn't happen because it rotates back and forth, but it is better than if it was straight up, because I'll show you, if it goes straight down, I'll just let it go like that. You can see how it like stops itself. Like it comes up, stops, and goes back instead of just coming up and then going back and forth. It kind of like buffers in that way. So that prevents it from over rotating, because if it was just up here, if the weight was up here, it would just seesaw back and forth. Like, see, I can't even do it with this weight because it just keeps stopping itself. So in short, having it like this allows a cleaner transfer of energy, because it's kind of stalled at the top instead of just being like. So that's it. That's all I got for you. Got it?
Let her rip.
Okay, that's one. 2, 1. Misfire. Strange. That was a good video too. It's so frustrating.